The lab we did for this presentation was the forced convection lab. It was conducted by myself, Michael, Dan, Hunter, and Jake. This is the outline for our presentation. It includes the introduction, measurements and methods, the results comparison, quality of data, conclusion with suggestions about how to do the lab. This is the introduction. Objective: to learn about and verify the conductive heat transfer coefficient. The goal of this experiment is to experimentally determine the conductive heat transfer coefficient and compare it to the value expected from the new Selk correlations in the heat transfer textbook. The applications for this apply to a radiator for a car engine, a heat sink for a computer, and a space heater for a room.
Methods and measurements. So the group assumed that steel had a specific heat of 0.466, an emissivity of 0.79, and a density of 7,900. So energy transfer was found by Q convection is equal to heat transfer by the surface area times T of the system minus T infinite. The group then used lump capacitance method using T minus T infinite divided by T initial minus T infinite, being found equal to the exponent of negative heat transfer by the surface area times density times volume times specific heat times time. The group found radiation heat transfer by HR equals emissivity times the Stefan-Boltzmann constant times T plus T sir times T squared plus T sir squared. This was for radiation heat transfer. The group found Newstead's correlation by Newstead's correlation equal to C Reynolds number to the power of M times Prandtl's number to the power of 1/3. C and M are part of the Hilpert's correlation. For theoretical H, we use Newstead's number times heat transfer times length over thermal conductivity. Measurements and methods continued. The group took rods and we measured them to find their specific size and to narrow down exactly what it was. We then used a pitot tube to find the velocity and pressure drop of the air in the air outlet at high and low speed configurations that were done by adjusting the cover over the fan blade. The rod was then heated to 500 degrees Fahrenheit in the oven. After it had reached that temp, it was cooled in the airflow till it reached 125 for low velocity and 100 for high velocity. The time was recorded every 25 degrees Fahrenheit. These steps were repeated for combinations of all the rod sizes and air velocities. So, high speed, small rod, high speed, large rod, low speed, large rod, low speed, small rod.
To start off the results, we'll begin with our graph to give a visualization of how the heat temperature changed over time. So as you can see, the smaller cylinder had the fastest heat loss because obviously it doesn't have as much mass and volume, and so it's not able to hold as much thermal energy, so it gives it off faster. And the next big thing is that the higher air velocity led to a way faster heat loss for both cylinders, large and small. And the reason that the higher velocity led to a faster loss of heat is because you're moving more air particles over the surface area of the cylinder, and you're able to transfer more heat that way. And as we can see on the graph, as the time goes along, the difference between the temperature of our cylinders and the temperature of the air, it starts out very large because the cylinders were heated to 500 degrees. And then as they cool down, that difference in temperature decreases. And then as the cylinders and the air temperature approach equilibrium, it slows down because it doesn't need to change as much as fast. Next slide, please. So using the lump capacitance model, we were able to find our heat transfer coefficient H. And then we ended up correcting this to account for the radiation heat transfer, because not all of the heat transfer in this lab was due to convection. The body that we were cooling down gave off radiation, and you have to account for that to get accurate results for heat transfer. And so to get the convection heat transfer, you have to subtract the radiation heat transfer on the right from your overall heat transfer coefficient on the left, and that'll give you your convection heat transfer coefficient, which will be shown on the next slide. Okay, so on the right, we have the corrected heat transfer coefficient for convection. And then on the left, we have our actual heat transfer rate. And so as you can see, for each of the cylinders, small and large, at both velocities, your heat transfer rate starts relatively large and it continues decreasing throughout the time. And that shows the same trend as our graph earlier, because as you have a large temperature differential, your your rods want to reach the same temperature as the surrounding air and each reach that equilibrium. So it starts out very fast, and then as it approaches equilibrium, it'll slow down, and that's why it shows a decreasing trend on the heat transfer rate graph. Next slide, please. Okay, and the final results slide before we get into air will be a comparison between the theoretical values from the fluids textbook versus what we actually got during our lab. So the graph on the left is that heat transfer coefficient corrected for convection from the last slide, and it's compared to our calculated H values based on the Hilbert correlation that Dan mentioned earlier. And so when we did the math, we got values that are quite a bit different from what we got in the actual lab. So they're off by about 20 to 30. And then the promising thing is that although they are off quite a bit, they do show the same general trend as the numbers. So our high velocity small rod has the highest H theoretically, and that's shown on the heat transfer coefficient for convection as well. So they are a little bit off, but they still do meet the trend. And so now we'll go on to uncertainty.
So in this slide, we are looking at the measurements that we took for the high velocity and low velocity using the Pitot tube. That has certain specifications from the factory about air. So the basic accuracy is plus or minus 1% full scale, and the linearity uncertainty has plus or minus 0.29 full scale. And so in the table below, you can see our high velocity and low velocity, and then we calculated the high velocity uncertainty and low velocity uncertainty for both basic and linearity uncertainty by multiplying them by the percentage. And then the random error on the far right is just based on the standard deviation of the standard deviation of the 10 measurements. Next slide. So for our quality of the data, for this lab, it was mentioned that a type J thermocouple has a bias uncertainty of 2.2 degrees Celsius or 0.75%. For this lab, we did not reach high enough temperatures where 0.75 would come into play. So our bias uncertainty for this lab is 2.2 degrees Celsius. And then below, we listed basically the calculations I explained earlier of timesing the velocity that we found by the 1% to get our basic accuracy, and the velocity times the 0.29 for the linearity uncertainty. And then there's our calculation for the random Pitot tube error, which is found by finding the TINV value, which can be found from a table or using an online calculator, times the standard deviation divided by the square root of the number of trials. Next slide. So in conclusion, our experimental data is not close to our theoretical data. However, they follow the same trend overall. As the rod cooled, they did so in an exponentially decreasing manner for all cases. For the small rod, high velocity, small rod, low velocity, large rod, high velocity, large rod, low velocity. The small rod did lose heat at a faster rate than the large rod. That was found to be a common trend between both high velocity and low velocity. And then both rods lost heat at a faster rate when subjected to a higher velocity. That was also found, or sorry, my bad about that. Having a human timer introduced inaccuracies, especially when the temperature was dropping at a rapid rate. So at the beginning of our trials, the temperature was bouncing all over, and it might skip 225. It might go from 226 to 223. And so where do you draw the line? Like, that made it hard for us to find the exact time. And the measurements were only putting out a reading usually every second, maybe twice a second. And so there's a decent bit of error that could be found there. And then having a sensor in the rod with a finer reading would help, like I mentioned, where if it updated more often, that could be more beneficial to having a more accurate time. And then we'll move on to the suggestions for completing the lab. So start up the furnace as soon as possible. When we entered the lab, we turned the temperature to max, but did not flip the switch. And so we ended up wasting 5 minutes on top of however long it took to heat up, because it takes like 15 to 20 minutes for it to reach a temperature where it could actually get the rod to the base starting temperature of over 500. And then as you get close to the end of the first 3 trials, put the other rod in so that it can start heating up to eliminate wasted downtime. And then for this lab, we had issues with our temperature sensor reading correctly. Sometimes you'd have to move the wire around in order for the temperature to be displaying a logical value. So be careful about this and keep a close eye on that. I think next slide. We'll take questions, but we don't have an audience to take questions. So I think that concludes our presentation.